Okay, we've been dealing with Riemann sums, uh, and we have our notation for our right-hand sum given here as the limit as n approaches infinity. What I'd like to introduce now is how we're going to connect this to what we've been doing with calculus with the derivative and antiderivative. Notice this next set of symbols here. This is our original formula is all using Greek letters. The summation is the sigma symbol here, but it's an S in essence, a Greek S for adding, summing things together. Delta x, we were using that for average rate of change, was what a delta y over a delta x. So these are our basically algebraic techniques with summation to calculate rectangles under a curve and add them together. And the idea was if you have more and more rectangles, you have more and more accuracy. So our jump into calculus is this new formula, which we're about to explore, is our fundamental theorem of calculus, where this is going to equal f of b minus f of a. But notice, one has a small f and one's a capital F, because in this formula, the function f of x, its derivative is equal to little f of x. That's important because when I'm going in this direction is with an antiderivative. So let's start with and see how this works, all this notation. So let's say I have some function f of x equals negative x squared plus 7. And this is a parabola opening down. And I'd like to know, let's take just a quick look at it. And it's important to recognize when we calculate area under a curve that technically those rectangles can be above or below the axis. They can be both positive and negative because we can deal with negative heights on those rectangles. But let's say I want to go from 0 to 2. So all this area here under the curve from x equals 0 to x equals 2. So the notation I would use to locate that would be this. And to calculate that area, we can now use the antiderivative. So this is actually going to be a two-step process. The first thing I'm going to do is take the antiderivative, and it will look like, let's see, negative x cubed over 3 plus 7x. And notice the symbol I'm using here. This is going to take us to allow us to do it in a two-step process. So step 1, take the antiderivative. Technically what you're looking inside of here is big F of x. You'll notice there's no constant, and we'll talk about that a little bit later. But you don't have to worry about the constant right now, and I'll explain why in a second. So what we're going to do is plug in. Very important to remember, this is our A value and this is our B value. So what we're doing, and just this part is my f of x. So we plug in B first. So we have negative 2 cubed over 3 plus 7 times 2 minus, make sure you use grouping symbols so that you distribute that negative correctly. Negative 0 cubed over 3 plus 7 times 0. I just plug it in 0 for x. So this is f of b minus f of a. That's what you're looking at there. So we have negative 8 over 3 plus 14, and all of this in the back is 0. If you'd like to, we can put this as a fraction by combining. So negative 8 divided by 3 plus 14 as a fraction is equal to 34 over 3. So in short, all we're doing is taking the antiderivative and taking the second value, plugging it in, and then subtracting, plugging in the first value, f of b minus f of a of the antiderivative. Now, you have to be clear on what you're calculating first of all. For instance, if I was to look at, let's say, a cosine function. I'm just making a rough drawing. So there's a cosine function from 0 to 2 pi. Let's say I looked at this. And so this is my accumulation from 0 to pi of the function cosine of x. Before we do our calculations, let's think about what we're calculating. We're calculating an accumulation, height times width, height times width. And that's fine to start off with. Actually, we'll start off calculating this area over here, and height times width, height times width, height times width. But once we cross this point, as we begin to accumulate, what you should notice is that all of your heights are negative. So your accumulation, once we cross that point, which is pi over 2, where cosine equals 0, all of these cosine values are negative, and that accumulation is going to cancel out your positive accumulation. So let's take a look at this. It should be obvious what I'm going to accumulate in total. You should be able to have a good guess what that's going to be. So let's go through the process. The antiderivative of cosine is sine. So I take the antiderivative, and we're going to evaluate that from 0 to pi. And we're going to evaluate that by first plugging in the sine of pi, and then I'm going to subtract, plugging in the sine of 0. Okay, so let's see. The sine of pi, you should recognize, is in fact 0, minus the sine of 0, which is also 0. So my total accumulation is 0. And let's talk about what happened there. When I got halfway, I switched from accumulating positive items to accumulating negative items. So I'm not actually accumulating area, I'm accumulating values, which can be both positive and negative. That's very different than if I asked you to accumulate area. So if we just focused on accumulating area, I would somehow have to recognize that all of this area is negative, all the accumulation is negative and have to compensate for that. I could do that, but that becomes a separate question. So let's look at that as a separate question. Say, I'd like to accumulate all of the shaded area. Okay, so first of all, I would have to recognize that it starts off as positive from 0 to pi over 2. And I want to add the second part. I'm going to put that in red, which is from pi over 2 to pi. But everything I calculate there, I realize is going to be a negative accumulation. So I need to switch the sign. Which means instead of saying plus a minus, I'm just going to subtract it. So basically, I'd be looking at two separate problems here. And that would be going from this antiderivative, which will be sine of x from 0 to pi over 2, minus sine of x from pi over 2 to pi. Let's see how this plays out now. Okay, so when I do my first, let me color code this. That might help a little bit. I'll just at least highlight it. I'm going to do this second part in green so we can keep track of the two different things we're doing. So first part. Okay. Sine of pi over 2 minus sine of 0. Minus, going to do the green part. Okay, so I'm subtracting. Oops. Back up. It's supposed to be green. Subtracting, plugging in sine of pi minus sine of pi over 2. Okay, so as we evaluate this, the sine of pi over 2 is 1, minus the sine of 0, which is 0, minus, still in parentheses, be careful about that, sine of pi, which is 0, minus sine of pi over 2, which is 1, gives me 1 minus a negative 1, or 2. So the total shaded area is 2, but the net accumulation of everything is 0. So be careful whether you're accumulating the functions or you're looking specifically for area, and that's a big distinction. So when I accumulate area and a function, I need to make sure that I know when I transition from positive to negative units. And that's what I was doing on this second problem. So that is the fundamental theorem of calculus and how you would handle it to also calculate area.